Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. So in the last couple of classes I talked about the silicon chemistry, and then in the today's class I am going to talk about organosulfur chemistry, and then after finishing organosulfur chemistry I am going to talk about the organophosphorus chemistry. So let's see what we are going to cover in the today's class. So I am going to cover, I think first thing is about the sulfur and its physical property. And then of course the different type of sulfur compound. I'm going to compare some of this between oxygen and sulfur, carbon, sulfur, their nucleophilicity, electrophilicity, and finally going to talk about the Lawson reagent. So sulfur is a tasteless, odorless, brittle solid, of course pale yellow in color. It's a group 16 element, period 3. You can see it comes after oxygen, the sulfur comes. So it is in the same group. It's a p block element, electron configuration. I think you guys are very familiar with that. And then the other important, so if you are seeing that in the oxygen sulfur in the same group, then you will see there are some property we are going to discuss also in a minute. And the other important thing is the chemistry. So you have sulfur forms over 30 different solid allotropes. Okay, more than any other element. That is very important. The most common allotrope is the octasulfur or cyclo S8, which is like a crown shape. Okay. So that is the most common allotrope of sulfur. So which is a crown shape and have a D4D point group and a zero dipole moment. Okay. Again, sulfur has 23 known isotopes, and 4 of which are stable, 32s, 33, and 34 and 36. Of course, the abundance of 32s is the highest compared to all of them. Again, I don't have to tell you, if you have done the practical in the undergraduate level, if you have seen the generation of the H2S generation, then you must have know that this is have a very bad smell. Okay, because of the especially the thiols is the one which have the worst smell compared to the even others. So not only so that is saying there, at the same time I should also say that sulfur is a very important compound, and it's present from very key proteins. It's present in key proteins, and like it presents in the glutathiones, it present in the amino acid. You can see we have shown here the glutathiones. You have so many thiols inside your body. Again, you can see sulfur is ingredient of FDA approved drugs. Okay, they are present in FDA approved drugs like dapsone, which is a water soluble products for leprosy. I think you all have heard about penicillin, the life saving antibiotic, also have sulfur present there. Sulfur is present in the fertilizer, fungicide, pesticide, used in the vulcanization of rubber. Sulfur based reagents are there. There are a lot of sulfur based reagents. You have used sulfur based solvent like DMSO every day in the lab. Okay. So in this particular class, I think what our plan is to learn about different type of sulfur compounds and some of the important reaction using organosulfur compounds. First thing we want to learn about the different type of organosulfur compound. First class is the thiol, which can be say RSH. Very similar to, if you think, as I said, I am going to compare with every time with the corresponding alcohol. So these are called alcohol. Now if you have a oxygen replaced by sulfur, we call it thiol. The important difference, I think, we're going to come back to that type of differences here, that if you try to compare their pK, we're going to discuss that also. So try to keep in mind that these are the important point we have to analyze. Now as soon as you are able to deprotonate the thiols, you can generate a compound called thiolate anion. It could be a different type of base can be used to make that corresponding thiolate anion. Then if you have a sulfur bond, this type of compound is called disulfide. Again, this can present in cysteine. You can see it's a cross-linked protein. So, and then sulfonyl chloride. I am going to discuss about sulfonyl chloride, which are very reactive, and it's a very good soft electrophile, which can also going to activate a olefin to form some sort of a 3-member. You can end up. I think we're going to talk about some of the reaction about the sulfonyl chloride in the after couple of slides. I think we're going to discuss that. Then I'm going to talk about the disulfide, means you have a sulfur with 2 R. If it is a 2 methyl group, then we call it dimethyl sulfide. Then there are sulfonium salt. Okay, once you have again, you can see this onium things counts, because you can see the sulfur from 2, now it is getting a positive charge on the sulfur. So it is becoming a trivalent with a positive charge. We call this sulfonium. Now if you have a sulfur with a oxygen bond, we call it sulfoxide. Okay, sulfoxide, the DMSO is the one of the important one we always used in the laboratory. It's called dimethyl sulfoxide. And then also we're going to talk about some of the other important reaction about the sulfoxide as well. Once you have a sulfur with a 2 bond with the oxygen, we call it sulfone. Okay, sulfone can be stabilizing the anion if you try to make the CH2. So this type of protons with the sulfones, you can be able to absorb those protons to generate a CH2 minus, which can be stabilized, so that can be participated in different type of reaction. I think we have heard about the sulfonic acid, sulfuric acid, and all different type of acids from sulfur. And then the last important thing is sulfonyl chloride. I think we always talk about this paratoluene sulfonyl chloride for the protecting group of the alcohol. It turns alcohol to a leaving group, not a protecting group, sorry. It is actually turning a alcohol to forming a OTS. By forming OTS, it is acting as a leaving group. Okay. So now we are going to talk about the different type of sulfur compounds, based on their valency. So it could be that the sulfur compound could be a divalent, could be a tetravalent, or could be hexavalent. Correct? You can see different type of examples here. We talk about already thiols and the disulfide, correct? And then we talk about, and here we talk about the, I think the sulfoxide, and then we talk about the sulfone, where sulfur is hexavalent. So we are going to introduce to you to the dimethyl sulfide. The dimethyl sulfide can be prepared from the methanol and H2S, can form dimethyl sulfide and water. It's a colorless, highly volatile compound with a cabbage-like smell. It's again a highly flammable organosulfur compound. The dimethyl sulfide can also used as a flavor and fragrance intermediates. Okay. It can also used, I think you guys are familiar that it can use for the preparation of dimethyl, the DMSO, which is the dimethyl sulfoxide. The starting material is the dimethyl sulfide, and then also it is going to form adduct with the boron can be able to sell as a dimethyl sulfide adduct. So as I said, the borons are highly reactive. That's why it is always sold as a adduct with a amines or with the dimethyl sulfide. Okay. Then disulfide. So if you have a sulfur, again we are in this type of compounds are called disulfide. And now again you can see this sulfur bond is weak. We can synthesize them corresponding thiol using an oxidant that can able to make the symmetrical disulfide. These are the common different oxidant, iodine O2 or H2O2. Okay, in the enzyme or in the equilibrium control, it can be also, there could be a unsymmetrical sulfide can be formed when the disulfide is interacting with the thiol. Then the other class of compound you can see about the thiol here, like cysteines here, which can also again as we said this can be used as a this can able to form a dimer, means forming this type of disulfide bridge linkage. Okay. So the disulfide linkage in the cysteine actually allows protein to retain their the 3-dimensional structure. Okay. After the oxidation happens. And again the thiophenol can be react with I2 to form the diphenyl sulfide, as I mentioned that the I2 can be used as oxidant. Here there is a Cl2 if you use, then that can also get back due to the phenyl sulfonyl chloride. I think I was trying to tell you that this is another very reactive sulfur compound which can use as a soft electrophile. Then the dimethyl sulfoxide, again from dimethyl sulfide, if you use an oxidant like H2O2, O2 or ozone or this oxidant, it can convert you to the corresponding dimethyl sulfoxide, which can use as a solvent. You can have some sort of you can have a vinyl and a phenyl. So this type of this species can be also get oxidized. The sulfur is getting oxidized in presence of MCPBA to form this corresponding sulfoxide. And in the previous case, you can see this type of sulfoxide, you have this vinyl group here, so that can be also get attacked with the nucleophile species. I'm going to explain some of the reaction also. Again, if you have these I think we're talking about sulfone. I talk about already dapsone, which is antibiotic, which is actually a prodrug for leprosy. So you can see there you can be able to take directly, you can be able to convert. So if you have this compound at the beginning, sulfoxide can be convert to sulfone, or you can start with the phenyl vinyl sulfide, and you can sequentially oxidize to first to the corresponding sulfur oxide and then to the corresponding sulfone. If you have a sulfinate like ArSO2Na, and you can react with ArCl to go to the corresponding sulfone as well. Of course, these are the very few methods. There are also more methods how you can convert them. So I think dimethyl sulfide is the starting point to if you want to get to the sulfoxide, or if you want to go to the corresponding sulfone. I think sulfur is much less electronegative than oxygen. That is the important difference. Staying in the same group, but the electronegativity sulfur is much less than oxygen. The sulfur electronegativity is very close to the carbon. You can see there is a very close electronegativity. So carbon sulfur bond is strong enough to be stable, at the same time is weak enough for the selective cleavage in the presence of much stronger carbon oxygen bond. That is important thing. So you have seen that if you have this the carbon sulfur bond, then you can able to cleave them. If you use ranitidicals during hydrogen, we have remembered you can able to cleave the carbon sulfur bond. Also there are other type of reagents which can able to do that. Again, you can see the average bond energy if you try to compare a carbon carbon bond versus a carbon sulfur bond, then the sulfur sulfur bond versus the carbon sulfur bond. The sulfur sulfur bonds are weak. You can see these type of compounds are also used. You can use this compound as a electrophile also. Okay, so because you can, once the nucleophile can attack here to the sulfur, it can also allow to cleave of this sulfur sulfur bond. Okay, I think that is the most important aspect here. And then the other thing is you can see this corresponding sulfur halide bonds are also weak. If you talk about these bonds like here, the sulfur with the carbon with the fluoride versus the sulfur with the fluoride, the sulfur fluoride bonds are weaker. And if you come to here, when you talk about the bond between this sulfur and sulfur, I think we already explained, this is the another weak bond. So this is I think a sulfur carbon bond versus the sulfur sulfur bond here. So this is the one, actually this is the one, the sulfur sulfur bond. Okay, so this is the one so this is the carbon sulfur bond, and this is the one, actually 301 is the value of the sulfur sulfur bond. So that bond is the weaker one, which I was trying to tell you, where if your nucleophile can attack, then it will cleave the sulfur sulfur bond. Again, the coordination number and you can see, and the oxidation state. I think we already talked about that there could be the divalent, tetravalent, and then hexavalent. So this is the oxidation state. Because of the d orbital of the sulfur, that's why it is allows to have this many different type of oxidation state, which will be difficult in case of oxygen, which don't have the corresponding d orbitals. Also you can see it can have a different type of coordination number as well. Okay, we have already talked about different type of compounds. You can see it can have a coordination number up to 7. But in this particular course, what we are going to talk about, majorly different type of organosulfur compounds, like you have seen the disulfide. Mostly we are going to focus on these 3 compounds, the disulfide, and then the sulfoxide, and the sulfone. So this is the part of this course. We are going to talk about these 3 different type of compound, different reactivity, and some of the important reaction using them. Again, sulfur versus oxygen. One of the important things, I think, if you have seen when you talk about a nucleophilicity, we always talk about that if you have a thiol, or if you have a you know, RSH, or we talk about RS minus, we have always seen these are the species you always use for the some of the SN2 transformations, and we always say that they are, you know, better nucleophile compared to alcohol, okay, or the corresponding alkoxide. So what is happening here now? If you try to compare there, if you try to compare the HOMO of sulfur versus the HOMO of oxygen, the HOMO of oxygen is energetically most, like, because oxygen is more electronegative. Once something is more, once the element is more electronegative, that can pull the electron density towards the nucleus, that can stabilize the corresponding HOMO. Now if it is stabilizing the HOMO, now you can see for becoming a nucleophile, they have to give the electron, the lone pair. So the energy for to reach the LUMO of the electrophile, if you see that if you know this is the LUMO of the electrophile, now you have to give electron density to the LUMO of the electrophile. Means if you want to go for a SN2 reaction, you have to give electron density to the sigma star orbital of the carbon halogen bond. In that case, you know what you are seeing here, the difference, because this is, you know, more stable, the energy difference will be higher here compared to in case of sulfur. Okay, the energy difference between the LUMO of the electrophile and the HOMO of the corresponding oxygen versus sulfur. Here the energy will be lower, so that's why the sulfur can easily able to, you know, donate electrons and act as a nucleophile. Again, the thiol versus phenol, I think the similar things comes here. Now we are talking about the pK value. I think one thing I told, you know, during the discussion, that if you have alcohol versus thiol, so you can see here we are talking about thiophenol. So once, you know, this is just a alkyl group, SH we call it alkyl thiols, like, and then once you have, you know, phenyl group, we call it thiophenol. So if you try to see about the pK, there is a huge difference in the pK between a thiophenol versus a phenol. Okay, and also you can see there is a difference between the, you know, as well as the alcohol and thiol also. You know why there is a difference? And again, you know, once you try to compare a pK of things, we always learn that we compare the, because anytime if you have the HA, we always talk about the other side is the, you know, the A minus, correct. So the HA can able to give H plus plus A minus. So to talk about that how strong the acid, we have to talk about the stabilization of the corresponding conjugate base. Okay. So now if you talk about the stability of different things, like you have this AR with S minus versus the AR with the O minus. So this AR with the S minus is the more stable compared to the S minus. So what is happening here? Because the larger size of the sulfur results the negative charge being distributed over a larger volume. So again, the sulfur is bigger in size, so that's why the negative charge will be being distributed over a, you know, large volume compared to oxygen. So in oxygen is smaller in size compared to sulfur. That's why the polarizability of the sulfur will be higher compared to oxygen. That is allowing to stabilize the charge compared to oxygen. That's why you can see the thiophenols will be, you know, having a pK value 6.62 in comparison to the phenol, which having 9.95. The other important aspect is if you have a, you know, if you take with NaOH and corresponding thiophenol, and, you know, so this is a ester from the alpha bromo acetic acid, a methyl ester. It is not happening that the NaO is going to come, the, you know, O is going to come and attack here. You are not going to end up getting to this product, but the NaOH can comfortably doing for the deprotonation to generate a S minus from here, and that can, that S minus can, you know, is very good for SN2 reaction, as I mentioned, and this is also a very good substrate for SN2. After the SN2 reactions, it will end up forming this product, okay, which is shown here in the mechanism. Sulfur compounds may be good electrophile and good nucleophile. We are going to talk about here that once you talk about this type of, you know, the sulfur compounds here. So this type of compound, once you treat with SO2Cl, what is going to happen here? It is going to form this the compound I think called I think the SrCl, we're going to come back to that compound called the sulfonyl chloride in the below. But here what is happening here in this mechanism, how this is happening, the sulfur is acting here, the lone pair is attacking to the the chlorine, forming this species here. And now, so you can see the one of the sulfur here kind of acting as a nucleophile. At the same time, the other sulfur is acting as an electrophile here. Because the sulfur bond is a weaker bond, so the Cl minus can attack to the sulfur, cleave the sulfur bond. That way it can generate this compound called sulfonyl chloride. Okay. So you can see it is generating the sulfonyl chloride here, and then this species which is forming here the rest of the compound which is forming after the cleavage of this carbon chlorine bond. What is happening, then generating this O minus, which can get rid of the SO2 can come out to generate a Cl minus. So after the formation of the sulfonyl chloride, I was trying to mention that this sulfonyl chloride can also act as a soft electrophile. That means if you have a olefin, you treat with the sulfonyl chloride, it can form this cyclic sulfonium salt. So it is going to form this cyclic sulfonium salt, because you can see sulfur with the three groups attached with the positive charge there. So this is not going to be stable. So the Cl minus, which is going to attack here, very similar to if you have seen the reaction with the the Br2 with the olefin. It is going to form there. It is from the the bromonium. Here it is forming corresponding sulfonium. Then the Cl minus is going to attack here to open this carbon, to cleave the carbon sulfur bond to form this product. And again, this is a stereospecific reaction, so that's why the product will be anti. Again, with increasing oxidation state, the compounds become hard electrophile as the positive charge on the sulfur increases. So what they are saying, that once you go from sulfur from disulfide to divalent to tetravalent to hexavalent, that means you see once the oxidation state of sulfur becomes 6, now this is become a hard electrophile. So now it is going to react with a hard nucleophile like alkoxide. Okay, so the alkoxide can react with that to get rid of the corresponding Cl. So that's how you are going to make the protection. What you are talking here, if you have this ROH and this the tosyl chloride, that means paratoluene sulfonyl chloride. So now if you have this you have formed the base can form the O minus, which can now attack here, okay, to get rid of the, so it is going to come back, get rid of the Cl to form this corresponding product. So now it can activate this OH for act as a leaving group. Okay. At the higher oxidation state, the sulfur could also be a good soft nucleophile. So we learned that higher oxidation state, sulfur become an electrophile. It could be a nucleophile. So what is happening here, but not. So you can see again the paratoluene sulfonyl chloride once you treat with the zinc powder. Now this is going to generate this anion here, because of this heterolytic cleavage of this carbon chlorine bond, you will generate anion. So because it is generating this anion, now it can become a soft nucleophile. So now it can attack to this allylic bromide to form this corresponding product, okay, through a SN2 reaction. So the other important thing I am going to talk about is the Lawson reagent today. Again, I think it is a very mild and convenient thiolytic agent to convert ketone, ester or amide to thioketone, thioester, thioamide. Okay, let us try to understand what we are talking. If you have this ketone, you want to convert it to corresponding thioketone, what do you use? Or if you have a thioester, you want to convert to the, you have ester, you want to convert to the corresponding thioester, what you do? Again the same question is, so if you want to do that, then what is your what will be your reagent of choice? Then we use the reagent called the Lawson reagent. Okay, so you can see this is the structure of the Lawson reagent. It was first invented by the 1956 by T.H. Chow and co-worker, although it was the first made popular by Seven Olaf Lawson. Okay. So in solution you can see the, although we talk about the, this is the structure of the Lawson reagent, but in the solution form it is stay as a more reactive dithiophosphenylide. So it is in the solution you find out it is stay as a dithiophosphenylide. Again you can see because it is forming this ylide stage, it is actually very reactive, and if you have this carbonyl compound here, the ylide can react with the carbonyl compound, okay, and then formation of this 4-member ring here, because it's forming this S minus and there is a plus on the carbon, so it can form this 4-member ring with this phosphorus, sulfur, carbon, oxygen. Then there is a decomposition of this ring going to happen, or disrupture of this happen, forming this carbon sulfur bond here, okay. So that is the important thing, that you are converting this carbon oxygen to carbon sulfur using this reagent called Lawson reagent. At the end also it is, you can see one of the driving force, if you think about that, you are actually getting cleave this. So I think this is the ylide you are forming. You can think about a carbon sulfur bond was replacing by a more stable a phosphorus and sulfur bond was replacing by using the phosphorus oxygen bond, okay. So that is the important thing here. I think again the phosphorus oxygen bond will be more stronger. That is the driving force for this reaction to take place. Here there is an example here. You can see once these reactions are also showing you that once you have a like carbonyl group, then it is not going to interact with the react with the ester. It is going to convert the corresponding ketone to thioketone. And once you convert the thioketone in this particular reaction, what is going to happen? You will convert this to corresponding thioketone, but at the same time this is this proton going to be abstracted to form the corresponding thiol that can attack to the thioketone, and it can going to form the corresponding thiophene. Okay. Another example here. So it is not only carbon. If you have a phosphorus oxygen bond, that can be also replaced by using Lawson reagent to the phosphorus sulfur bonds. So in this particular class I talk about the sulfur and its physical properties. I introduce you to the different sulfur compound, the thiophenol, the disulfide, and then also comparison of sulfur with the carbon and oxygen. I talk about the nucleophilicity and electrophilicity of sulfurs. You have seen once you have this type of compound, sometimes you have seen these are this can also if one of them is acting as a nucleophile to form some sort of a positive charge there, some sort of a sulfonium, then the nucleophile can come and attack and break this bond. So that means at the same time this is a nucleophile as well as this is a electrophile. I think we talk about that. And then also I introduce you to the Lawson reagent, where you can able to convert. Majorly you will see this reaction that a carbonyl group to you introduce a ketone to a thioketone. You can again here are the references. Mostly I think you see the the course is covered from this book of Organic Chemistry by Jonathan Clayden. Okay, you can go through the chapter there. Again, thank you so much for coming to the class, and we are going to talk about more sulfur chemistry in the next class. Thank you.